This is part one of two lectures on Morse theory and specifically Morse functions. In this first lecture, we are going to begin by talking about smooth functions. We will then talk about critical points of smooth functions. Next, we will talk about a specific class of functions called Morse functions and how they are defined based on the property of their critical points. We will then study an important result in Morse theory called the Morse lemma. We will then talk about associating an index to every critical point called the Morse index and see how this helps classify critical points. In the second lecture, we are going to cover extensions of these ideas to piecewise linear functions. Let's begin by talking about scalar functions, the topic of today's lecture. We are going to restrict ourselves to simple domains initially. The more familiar Euclidean space in 1, 2, and 3 dimensions, so R, R2, and R3. Here are graphs of simple scalar functions. Note that these are graphs of scalar functions. So, for example, a sinusoidal curve is actually defined over a one-dimensional domain, namely the real line. Similarly, what you see on the right are graphs of two-dimensional functions. In order to define a critical point, we need the notion of a gradient. So the gradient del f is essentially a vector of the partials of f with respect to the different axes. The gradient going to 0 is the condition that we need to check to determine if a point is a critical point or not. We call f a smooth function if the second partials are actually defined. So essentially we want the function to be twice differentiable in order to call it a smooth function. Now, why are we studying functions? So far we were studying topological spaces. Why study functions? Let's try to answer that question first to set the context. Like I mentioned, we have been studying topological spaces, but so far we have been studying them via invariants. We have been studying Betti numbers, Euler characteristic, homeomorphisms, homology, and homotopy. These were different invariants that we have studied, some in more detail than others, right? So maybe one quick exercise for you here. You would notice that I have listed the invariants alphabetically. You may want to try to reorder them in terms of how strong this notion of invariant is, right, towards the weak. So a strong notion will imply a weak notion. That's what we mean by strong to weak. So try to reorder these invariants from strong towards weak. So these invariants, as we saw, some are easily computable, others like homeomorphism is not easy to compute. Nevertheless, it's a useful invariant to distinguish topological spaces. For those notions such as homology and Betti numbers, we also saw an algorithm to compute, for example, the Betti numbers. In order to compute the Betti numbers for a topological space, we needed the topological space to be represented by a simplicial complex. So this simplicial complex was essentially a triangulation of the topological space. Now what we want to do is to study the topological spaces via real valued or scalar functions defined on the space. So this is where Morse theory comes in. So essentially we want to study the relationship between critical points of this real valued function and the topology of the domain. So the first motivation is essentially what I said just now, right? So namely, we would like to classify topological spaces. We would like to understand the shape of this topological space and study its properties. And the way we want to do this is by defining functions on top of the space. There is a second motivation for studying Morse functions and Morse theory. And we will try to focus on this aspect as well in the future lectures. So the second motivation is that this study of relationship between critical points and the topology of the domain helps us study input scalar functions. Now scalar functions are often used to represent scientific data. So Morse theory provides us a tool for studying scalar functions. It helps us capture important properties of the scalar function. It helps us identify patterns in this scalar function by discarding the geometry and abstracting away the important topological features. So this is an important role that Morse theory plays in the study of scalar functions and hence in the study of scientific data. Before jumping into Morse functions and its definitions, let's take a simple example to understand what we are trying to study here. So here is a graph of a 1D function. Our aim is to understand its critical points. Right? We all know the definition of critical points from calculus, but let's keep that aside for a bit. Let's look at this graph of this 1D function as some kind of a roller coaster ride. Let's think about how stable we are at any point on this graph, right, or on this roller coaster. So for example, if you are at some point which looks like, so for example along at some point here, you know that you are not stable in the sense that you gravity acts on you and you start sliding down, right? Whereas if you are at this point, right, so this point which is a local maximum, or you are at this point a local minimum, then you know that you are stable in the sense that you remain at that point unless somebody pushes you one way or the other. So so this essentially means that the critical points capture some notion of stability of the point, right, and hence the stability of the point with respect to the scalar function. In this case, the scalar function is essentially just the height function. So let me state that again. So the critical points are exactly where the ball remains stationary, right, or you as a rider on the roller coaster you are stationary if you are not under the influence of any force, any external force, right? Now, what is the difference between minima and maxima? So again, let's try to explain this via the notion of stability. The maximum is a stable location where if you are pushed one way or the other, you move away from the point and do not return to that point. So in this sense, the maximum is an unstable. It's an unstable critical point. The minimum, on the other hand, is stable. So if you perturb a point away from the minimum, under the influence of gravity, this point comes back, or the ball comes back, rolls back into the minimum. So in that sense, the minimum is stable. So this is one notion that we will use to further classify the critical points. Now you may want to try and think about what this means in terms of the first derivative, second derivative, and so on, right? So essentially what we have said here is critical points capture the stability of points, and further classification of the critical points requires us to talk about whether the critical point is whether the point is stable under perturbation or not, right? So we know that this can be captured via the second derivative test. So far I have stayed away from so-called degeneracies. So you already see that there is one degeneracy shown here in the brown box. So there are additional points such as this point where the gradient is 0, right? So of course I didn't explicitly say this, but the maximum and the minimum are identified by the gradient equals 0 condition. So there are other points such as this inflection point where the gradient goes to 0. But let's think about how stable this particular point is under perturbation. So what happens if I perturb a point lying at this inflection and push it towards the left? So in this case, the ball rolls back, or the point rolls back to the critical point. But if I push or perturb the point towards the right, then it rolls away, right? So it seems like this does not fit either of the two conditions, right? So this is what we call a degeneracy. So we already know that this particular critical point is called degenerate because the second derivative at this particular point is 0. So it does not uniquely tell us whether the critical point is stable or unstable, whether it is a minimum or a maximum. This is a third type of criticality. It is a degeneracy, right? These are difficult to handle. So what we will do is to consider functions that do not have such degenerate critical points. Right? So here is the definition. F, the function f, is a Morse function. So this is so I have not stated a few properties here. We assume that we are always talking about differentiable functions. So f, a differentiable function, is called a Morse function if none of its critical points are degenerate. Right? So that's the definition of a Morse function. Let us now move to 2D to see how this idea extends when you have a function f defined on the plane. So here we have a picture of a 2D function. So it's essentially a graph of a 2D function, and you can see that the critical points are already labeled here. Right. Let's look at the simple critical points, namely the maxima and the minima. Right. Again, let's go back to the notion of stability without external force and stability under the action of external force. So if you place a ball anywhere on this terrain, it starts rolling down under the influence of gravity, unless it is at one of these points shown here on the surface. So namely one of the blue points, one of the gray points, or one of these points which are part gray, part blue. The blue points are the local maxima. The gray are the local minima. Right? Let's look at these first. So these are characterized by the gradient equal to 0. Right? So the gradient at these points is equal to 0. So I hope you know what this gradient notation means, right? So this del f is essentially a vector of the partials with respect to x and y. So the critical point is where this gradient is equal to 0. Now we can further classify the critical points based on how stable this particular critical point is. So namely, under the influence of some external force, what happens to the ball located at that particular point. So again, if you are at a maximum, what happens is that if you push the ball in any direction, then it rolls away from the maximum. So hence this particular point is highly unstable. So it's unstable in two directions, in both the x and the y direction. The minimum, on the other hand, remains stable, again in both directions, the x and y direction. So if you roll the ball away either in the x direction or in the y direction or somewhere in between, the ball rolls back to the minimum, right? Now in 2D we have an interesting third configuration, namely the saddle, that is shown here in using this new glyph, right, which is partially gray and partially blue. So these saddle points are where the function is stable in one direction, namely the x direction, and it is unstable in the other direction, namely the y direction. So these critical points are called saddle points. So they are called saddles because the location here looks like a saddle, a horse's saddle, hence the term saddle, right? Again, you can have degenerate critical points in 2D, right? Now, how do you test for these critical points and degeneracies? Again, a critical point is where the gradient is 0. The second derivative helps us decide whether the critical point is a minimum, maximum, or a saddle. I will come to that soon. So this second derivative is, since it's a 2D function, the second derivative can be written in the form of a Hessian matrix. You may have seen this before. If not, it's a very simple matrix representation of the second derivatives, the second partials. So for example, the second partial of f with respect to x, or with respect to x followed by y, and so on. So the Hessian, we want the Hessian to be non-singular, namely its determinant should be non-zero. So in this case, we will be able to further classify the critical points. If the Hessian is 0, then we are, so this corresponds to the degenerate case. So this is what we call as the Hessian test. Right? So essentially, if the Hessian is singular, then we know that the rank of this matrix is less than 2, right? So the rows and the columns are not linearly independent anymore. Let's look at the case where where at the critical point the point passes the Hessian test. So namely, the Hessian is non-singular, right? Then we know that this particular matrix has two non-zero eigenvalues. How do you use the eigenvalues to classify the critical points? So note that the critical point here, the maximum, was unstable in all directions. So this will actually correspond to two negative eigenvalues. So the max will correspond to two negative eigenvalues. Whereas the saddle will correspond to one positive and one negative eigenvalue. And the minimum will correspond to two positive eigenvalues. Right. So essentially, what we see is that the min, max, and saddle can be classified by looking at the number of directions in which the function goes down in its neighborhood. The same analysis holds in 3D as well, right? So you have the Hessian now is a 3x3 matrix. Again, the critical points are classified based on the number of negative eigenvalues of the Hessian. Again, we do not want degenerate critical points. So we want the Hessian to be non-singular. And again, we call f as a Morse function if none of its critical points are degenerate. Let's look at some examples now. So here are three examples, three different 2D functions, f of xy equals x squared plus y squared and so on. And what I have shown is the origin located here, for example, for x squared plus y squared and so on. So as an exercise, try to convince yourself that the origin, that is 0, 0, is a critical point for all three functions, and try to classify the what type of criticality the origin is for these three functions, right? So try that as an exercise. Maybe you can pause and try that. So if you have done this exercise, you will recognize that for the first function on the left, the origin is a local minimum, and it has two positive eigenvalues. The next here, for the second function, you have two negative eigenvalues. So the critical point is a maximum. And here you have a saddle with one positive eigenvalue and one negative eigenvalue. So these are three distinct neighborhoods for the three types of critical points that we have seen so far for 2D functions, right, or functions defined on R2. Now it turns out that this is not just an example, but this is actually the rule. So the Morse lemma actually writes this particular result more formally. So let's look at the Morse lemma. Let's call this particular point that we are studying as p sub 0, right? So let p sub 0 be a critical point of a Morse function f that's defined on a surface. For now we are looking only at Morse functions defined on R2, but this Morse lemma holds in general, right? It's just that the expressions become longer, but there are no additional conditions. The lemma is as simple as it is stated here for higher dimensional domains as well. But let's focus on the 2D case here. So let p sub 0 be a critical point of a Morse function that's defined on a surface. Let's also assume that f can be expressed with respect to some local coordinates, right? So by local coordinates, we will talk about local coordinates later. But for now, let's assume that xy denotes the two coordinates for R2, right? So what the lemma states that f can be expressed in the neighborhood of the critical point in one of these three forms, right? So it says that f behaves either as x squared plus y squared plus a constant, or x squared minus y squared plus a constant. This is the saddle case. Or minus x squared minus y squared plus a constant. This is the maximum, right? So this lemma says that if you plot the graph of f within a small neighborhood of a critical point, then f looks exactly like one of these three cases and nothing else, right? So either it is an upward paraboloid or the downward paraboloid or this saddle surface. So this is a very strong result, right? So this is very strong in the sense it says no matter what function you choose. So the function f, remember, can be any polynomial, any differentiable function. But within the neighborhood of a critical point, it is quadratic. Within a small neighborhood of the critical point, f is exactly a quadratic function. So this is a very strong result, right? So this is what the Morse lemma says. We will take this result without proof. The proof is beyond the scope of this particular course. But we will look at the implication of the Morse lemma, right? So that's what we will do next. So remember that the topic of this lecture was to try and understand critical points of scalar functions. So we already know that the critical point can be identified by studying its gradient, right? And essentially looking at all the points where the gradient goes to 0. We were further interested in classifying the critical points. So we were asking the question, how many types of critical points do we have? How does this relate to the types of instability? How many types of instabilities is possible, right? And we saw that the Morse lemma answers these questions. It actually gave a classification by stating that in the neighborhood of a critical point for a 1D function, the function can be either written as x square or minus x square. There is a constant term that I am ignoring here. For two-dimensional functions or bivariate functions, the function can be written either as x square plus y square, minus x square plus y square, or minus x square minus y square. Similarly, for three trivariate functions or three-dimensional functions, in the neighborhood of a critical point, the function can be written in one of these four different forms. Right? If you count the number of negative signs here, this gives us a number that we can associate with each critical point. Right? So in the case of 1D functions, a minimum has this index 0, a maximum has the index 1. In the case of 2D functions, a minimum has again an index 0, the maximum has an index 2, and the saddle has an index 1. So note that the index captures the number of negative eigenvalues, right? Again, in the case of 3D functions, the indices can go from 0 to 3, that's the dimension. 0 corresponds to minimum, 3, that's the dimension of the domain, corresponds to the index of the maximum. And you have two other types of criticalities. These are called saddles. To distinguish between the saddles, we call them as one saddle and two saddle, right? So using the index as a prefix. So now we have a classification of critical points. And if we have the representation of the function in the neighborhood of the critical point, we can easily determine what type of critical point it is. So far we have been looking at functions defined on Euclidean spaces. This was more familiar. Let's now try to define these functions on general topological spaces. We are not going to go all the way and define them on a generic topological space. We are going to restrict our attention to so-called manifolds. So let's understand what manifolds are and why they are important. The Euclidean space is a very special case of a manifold. So R, R2, R3, these are one-dimensional, two-dimensional, and three-dimensional manifolds. A manifold in general, however, is a space that is locally Euclidean. What does that mean? This means that if you are an ant living in one of these spaces, right, you don't have a worldview. You get to see only the neighborhood, only the local neighborhood of yourself, right? And if your local neighborhood behaves like the Euclidean space, then you call the space as a manifold. Let's look at examples and then look at a formal definition. A circle is a one-dimensional manifold or a one manifold. Why so? If you take any point on the circle and you take a small neighborhood of this point, right? So this neighborhood will look like this, right? So it will look like, so there will be a small piece of an arc, right? Maybe I will so there is a small piece of an arc. We know that this arc is homeomorphic. So we have studied homeomorphism. We know that this arc is homeomorphic to an open interval. So there is a continuous one-to-one bijection whose inverse is also continuous between the arc and the interval. So this property is true for any point on this space, right? And hence this particular arc, this particular space, the circle, is called a one manifold. So the formal definition follows from this example, right? A space M or M2 or M3 is a manifold if for every point X within that space there is an open set containing that particular point that is homeomorphic to the Euclidean space R, R2, R3, or in general Rd, right? So I'm not going to state this and write this down, so it's available in the notes, but let's look at examples. The idea is to understand these notions and then try to use them. The sphere is another example of a manifold. If you are on the surface of the sphere, then your neighborhood looks flat, right? Like R2. So hence the sphere is a two manifold, a two-dimensional manifold, right? So the sphere is a two manifold. Most surfaces are two manifolds. A torus is a two manifold. The neighborhood of any point, a small enough neighborhood, looks like the plane. Of course, the neighborhood looks like a distorted version of the plane, right? But there is a continuous map F that takes the neighborhood of this point P to R2, right? So hence the torus is also a two manifold. We will restrict our attention to such topological spaces in the future lectures, right? The space of all manifolds is broad enough that it captures many real world scenarios while not being restricted to something like the Euclidean space. What remains to be done is to introduce functions on these manifolds. So there is a very simple way to introduce functions on these manifolds. We can always think about these manifolds as lying in some Euclidean space. For example, this surface here with two tunnels, well, actually more tunnels than that, but two, the genus 2, right? There is one genus here and there is one more here. Maybe as an exercise you can try to compute the number of tunnels in this topological space and these two legs, right? So this is a surface. Let's assume that this is embedded in 3D space, as you see here, right? The function defined on this surface is essentially the third coordinate, which is the vertically upward direction, as you can see here, right? So this is a simple way of defining a function on a manifold, and any point on the manifold in this case has three coordinates because it's embedded in 3D. But we know that the local neighborhood of this particular point looks like R2, right? So there is essentially only two coordinates required to parameterize this neighborhood. The gradient can be defined using these local coordinates. So hence the gradient is defined at every point. Note that we want the function to be twice differentiable, so we'll assume that that is true even here, right? So the definition of Morse function holds even for the case of functions defined on manifolds, right? Because we have the notion of gradient, we have the notion of twice differentiable. So we call f as a Morse function if none of its critical points are degenerate, right? Let's look a little bit at why it is justified to talk about this restricted class of Morse functions, right? So let's consider f here, right? The function f has many critical points which are actually shown on the surface here. Some of these critical points are minima. For example, this is a minimum, and there is another minimum here, which is the leg. There is a maximum somewhere at the top, right? And the remaining critical points shown with black dots are saddles. Either one saddles or two saddles. That's something you have to decide, right? So it's actually a trick question. F is only a two-dimensional function, so you can have only one type of saddle, right? So remember that even though your surface is embedded in 3D, the surface is actually a two-dimensional manifold. So hence f, the function defined on it, is also two-dimensional. So it can have only three types of critical points. Okay, so that was an aside. Let's come back to the discussion on why it is okay, or why is it justified to talk about Morse functions, right? So remember, a Morse function is a smooth function, none of whose critical points are degenerate. So it turns out that f, any smooth function, can be always perturbed a little bit to become a Morse function. And this perturbation can be made as small as necessary, right? So for those of you who have done some real analysis, I will state this formally. For those who don't, I will try to give an intuitive description. So we know that the Morse functions are dense in the set of all smooth functions, right? So intuitively what this means is, if I have the space of all functions, so let's say this is some arbitrary space, right, whose points here, right, the points inside this are, each point corresponds to some smooth function, right? So what this property says is that you take all the space of all Morse functions, right? Then what happens is, if you pick any point here, you know that this point is a Morse function. You know that there is a Morse function in a small neighborhood within a small neighborhood of the point that you have chosen, right? And since the perturbation can be made as small as necessary, you know that you give me any small neighborhood, I can find a Morse function within that neighborhood, right? So this is what this notion of dense means, right? So in practice, it's okay to assume that your function is always Morse. because you can perturb your input function just a little bit to make it a Morse function. Right? So from now on, we will assume that all the functions we are working with are Morse. And while talking about algorithms, we will also discuss how we will handle this in practice. So I want to end the discussion today by talking about critical points again, by talking about classifying critical points using so-called isocontours or isosurfaces. This is yet another way of classifying critical points. Comparing and contrasting these different methods helps you understand critical points better. So an isocontour or an isosurface in general is essentially the pre-image of a particular scalar value C, right? So given a Morse function f, the pre-image f inverse of C, a real value, is called an isocontour or an isosurface in general. What we are going to do now is to study the isocontour or the isosurface in the neighborhood of the critical point. Right? So let's start with a 1D function. So here we have iso points. So a 1D function, what we've shown here with the dotted curve is the graph of this function. So here we have a minimum, right? So let's look at f inverse of C, where C, the scalar value, is smaller than the value at the minimum. So that's why before, right? So before I hit the scalar value of the minimum, what does my isocontour, so well, they are called iso points in this case, but what do my iso points look like? So within the neighborhood of the minimum, none of the points have a value lower than the minimum, right? So f inverse of C is actually empty in this neighborhood. So which is why you don't see any iso points. Whereas once you cross the iso value or the value at the minimum, then f inverse C suddenly gets two components, right? So these two black points, these are points at that correspond to f inverse of C, where C is greater than the value at the minimum. Let's look at the before after picture for a maximum. So the maximum behaves in exactly the opposite way. So before, that is, you hit the scalar value of the maximum, you get 2 points, iso points. After you cross the scalar value of the maximum, none of the neighborhood points have a value that is greater than the maximum. So remember, we are looking only at a small neighborhood. Let's look at this before after picture for a 2D function. So in 2D, one way to think about what we are doing is imagine a terrain and imagine water level rising up, right? So from a low value to a high value. And we are trying to find out what is the water level before it hits a minimum, maximum and a saddle, right? So again, the neighborhood is shown here as a disk. We are now looking at a minimum. So before you hit the minimum, the neighborhood is shown with the disk and the isocontour is empty, right? So the water level has not reached the neighborhood, right? So after it touches the minimum, then the water level rises up. So F inverse of C for values greater than that of the minimum will look like a circle here. Let me restate that in a language that we are going to use later. Before I hit the minimum, the isocontour has 0 components. After I cross the minimum, the isocontour has 1 component. In the case of the maximum, before I reach the maximum, the isocontour has 1 component. After I cross the maximum, the isocontour has 0 components. What happens at a saddle? Let's look at the before picture. Let's look at only the solid part of the isocontour initially. So before I cross the saddle, the isocontour has 2 components within that disk neighborhood, right? Globally, this isocontour may have 1 component, but locally I seem to see that there are 2 components, right? So if you focus on just the solid black arcs, the after picture also looks similar. After I cross the saddle, again within the disk, the isocontour has 2 components. What distinguishes the two is how the isocontour is connected globally, right? So now let's look at the isocontour globally. So before I cross the saddle value, the isocontour had 1 component. After I cross the saddle, the isocontour has 2 components. So the number of components has increased. Of course, the isocontour could have been connected differently in the before picture. So here is the same isocontour in the neighborhood, but it is connected differently outside of the neighborhood, right? What happens in this case? After I cross the isocontour, with the same global connectivity, the isocontour becomes 1 single connected component, right? So let's restate the condition. For a saddle, either the number of isocontour components increases by 1, as in it goes from 1 to 2, or it decreases by 1. So the isocontour components goes from 2 to 1, right? So in all 3 cases, minimum, maximum and saddles, you can distinguish the type of criticality by studying the isocontour components before and after you cross the critical point, right? So we will see in the next class how this translates to an algorithm, right? The key observation is that the topology as captured by the number of connected components changes upon passing a critical value, right? Upon passing through a critical point. Like I said, this is the property that we will use to classify critical points. Since we have already seen multiple ways of classifying critical points, here is yet another way via so-called gradient lines. So looking at the gradients in the neighborhood of the critical points. The gradient in the neighborhood of a minimum will all point outwards, right? And the gradient in the neighborhood of a maximum will point inwards for a 1D function. For a 2-dimensional function, for a maximum on the left, all the gradients will point towards the maximum. The function is increasing towards the maximum. On the right, what you see is the gradients for a minimum, they will all point outwards from the minimum, right? In the neighborhood of the minimum, the gradients all point outwards. The saddle has a very interesting picture. There are two directions. There are two directions in which the so along the x direction, for example, the gradient is going in towards the saddle, whereas in the orthogonal direction the gradient goes away, right? So if you look at the number of independent directions, there is one direction in which the gradient flows towards the critical point, and there is one direction in which the gradient flows outwards, away from the critical point. So again, the gradient lines seem to help us distinguish between the types of critical points. Let's do this exercise for 3D. So again, for 3D, the critical points, there are 4 different types of critical points, remember. For a minimum, the isosurface now, before you cross the minimum, is empty. After you cross the critical point, the isosurface gains one component. So the isosurface in particular looks like a sphere. So this is a minimum. The maximum behaves in the opposite way. There is one component of the critical point, one component of the isosurface before you cross the maximum, and after you cross the maximum, this component vanishes. The saddles here you have to imagine a little bit. There are 2 types of saddles. For this saddle, right? Let's look at one saddle. Before you touch the one saddle, the isosurface looks like this, 2 conical caps. Remember that these conical caps can be connected in different ways globally, right? I don't want to draw this, but you can imagine that this conical cap on the top is connected to the conical cap in the bottom to form something that's close to a torus, right? Not yet a torus, but a torus. Once you cross the one saddle, these 2 conical caps merge, right, into this funnel-like shape, this hourglass-like shape. Now globally what happens? You actually form a torus. So essentially, the number of connected components do not change. It was 1 earlier and it remains 1 because of the way this the conical caps were connected. But before you cross the one saddle, you had almost a torus, so there was no tunnel. But after you cross the one saddle, the isosurface is actually a torus, so there is a tunnel. So again, the topological invariant Betti numbers can be used to classify the type of critical points. The 2 saddle behaves similarly. The before picture looks like the hourglass, and the after picture looks like these 2 spherical caps, right? So essentially, the number of tunnels again changes from initially it was actually a torus to later there is no torus. So this is a 2 saddle. So we haven't yet talked about an algorithm. We will do that in the next class. But let's finish this discussion by talking about the gradient lines for 3D functions. So again, for a minimum, in the neighborhood of the minimum, the gradient lines all go outwards. So this looks like a source, right? So all the gradient lines go out from the minimum. For a maximum, all the gradient lines flow towards the maximum. And for a saddle, there is one direction in which the gradient lines flow in, and other directions in which the gradient lines flow out, right? So this is a one saddle. And a two saddle, where the gradient lines flow out in one direction. There is a zoomed in version. The gradient lines flow out in one direction, the vertical direction, and they flow in two directions, the x and y directions. So far we have been talking about smooth functions and how to classify the critical points. In order to design an algorithm, we first need to represent the function, represent the space, the domain of this function. So we will start with that discussion on representations of the domain and the functions before talking about algorithms for classifying the critical points. Let's continue that in the next lecture.